we present a method that extracts a compositional program from a demonstration sequence or oracle model. We believe that compositional control is key to practical robotics. End-to-end learning is effective, but controllers lack flexibility and interpretability. For example, consider applying end-to-end learning to the inspection task here. What happens if we want to change the inspection order, or if a user asks what will happen next? In contrast, compositionality allows for flexibility and interpretability. We present a method to infer compositional controllers from an oracle model. Here we infer the goal states and controller gains for a hybrid system comprising of switching proportional control laws. Inference under this model is challenging, so we use model sensitivity analysis to bias the inference towards controllers whose goal states correspond to important visual content. So how do we do this? Well, we start from a demonstration sequence and a model trained using your favorite end-to-end learning method. We then infer the controller parameters, in this case controller gains and goal states in joint angle space, that best fit the demonstrated visuomotor observations, using sequential Monte Carlo, with a rejection sampling step that prefers projected controller goal angles that correspond to visual content of significance to the model. We then cluster these inferred controller parameters to identify the set of controllers used by the demonstration. So here, you see that we identified 5 distinct controllers, which correspond to the various objects being inspected. These clustered controllers can be used to produce a symbolic controller trace, which is the sequence of controllers required to reproduce the behavior. We treat this controller trace like a string, and search for common structures expressible using our proportional controller grammar. By identifying repeated structures like loops and palindromes, we simplify the trace to produce an actual program. A loop is just a repeated substring, while a palindrome involves moving through a sequence of states and then reversing out of these in order. This program is easily modified by an end user, but still lacks generalizability, as controllers in the program are tied to fixed joint angle goals. In order to address this, we take advantage of the fact that our approach is biased towards goals corresponding to visual content, so segment and crop the content around goals to produce synthetic datasets of images and corresponding joint angle states. We use this data to train new perception networks that predict the goal state for each controller. This allows for more flexible use. For example, here, where we have reordered the objects for inspection and can still execute the original program. Given the program and this controller grounding, executing the program is simply a matter of calling the appropriate proportional control law at each step, with the reference goal state predicted by the grounding perception network. It is important to note that this is a classic and trusted perception action control loop. So, to summarize, we explain behaviors using hybrid systems of proportional controller sequences. We infer these controller parameters using sensitivity analysis priors and sequential Monte Carlo. We use these controllers to synthesize a program and visually ground controllers via prediction networks predicting goals. This program is flexible, generalizable, and importantly, interpretable.